Welcome to Lesson 8C, Measuring Wall Loss Coefficient. We're going to look at how to actually measure the wall loss coefficient, and then I'll do an example. Let's think about how you might do this. Suppose we have some kind of a source here or some material that you want to see what the wall loss is into it. So you set this up, same room as before, and we have some surface area of this object that we're interested in. Here's the procedure. You put a large concentration, so C is big, or whatever contaminant, at T equals 0. So you might imagine letting S source strength be on for a half hour or something and put a lot of chemical into this room. And so C keeps rising. And then at T equals 0, you turn off S and turn off all ventilation. So in other words, there's no Q, there's no S, there's nothing coming out. You basically seal up this room, or it can be a flux chamber actually, just a box. You seal it up. We'll still assume it's well mixed, so we have the fan there. And so all you have going on is this wall loss into the surface. We'll assume that there's negligible wall loss into the actual surfaces of the box itself or the room. So this is what we're measuring, this yellow object I have drawn here. You also would put some kind of a probe to measure C as a function of time, and we assume it's well mixed, so it doesn't really matter where here you measure that.
This is like a flux chamber without the flux, yeah?
Yes, Albert, I suppose it is.
Yeah.
Now let's plot C as a function of time. And what do we expect? Well, this is a first order system, and so we expect you would start at some initial value C0, and we would expect it to decay. If it's an experiment, there's going to be scatter. And when you actually do this, you'll find that the scatter gets pretty bad when you're at these very low levels, because it's very hard to measure C when it gets real small. You may only have one significant digit of accuracy on your readout here, or your computer data acquisition system. So this will be exponential decay, first order. If all the equations we derived last time are still valid, this will be a first order ordinary differential equation. So how do we analyze this? Again, it's a first order ODE, and so we'll use the equations from the previous lecture module, which were CSS minus C over CSS minus C0 equal E to the minus AT. That's our main equation for any time T. What are the other variables? Coefficient A was Q plus KW AS over V. And here, Q is 0, so A is equal to KW AS over V. B was S plus Q CS over V. Well, here, S is 0 and Q is 0. There is no CS because you're not bringing any supplier into the room. It's sealed up. So Q is 0 and CS doesn't matter. In other words, B is just 0. And then CSS in this equation, if you look back, was equal to B over A. Well, B is 0, so CSS equals 0. Well, I could have saved you a lot of trouble here in the math. If we just look at this plot, we know that as this thing decays, there's no source. We've shut the source off, and all this contaminant is eventually going to get adsorbed into the object. So CSS, we could have said right from the beginning, is going to go to 0. But at least we proved that mathematically. Now let's solve for C of T. Turns out to be C at 0 times EXP of negative KW AS T divided by V. So we have an analytical expression for this curve. Now the problem is when you have experimental data, you need to do some kind of curve fit to this equation, and that looks like a challenging thing to do, but we can turn this into a straight line. First, I'm going to recall some math equations. Log of AB equal log A plus log B. This works for natural logs too. Natural log AB equal natural log of A plus natural log of B. Natural log of E to the something, let's call it Z, is equal to Z itself. Here's one that you probably don't remember from math class. Log 10 of some variable x is equal to natural log of that variable x divided by natural log of 10. That's how you convert between natural logs and logs. So we have these equations that we'll use to manipulate this equation. So how am I going to do that? Well, first I'm going to take log 10 of both sides. And so this equation becomes log 10 of c, not c of t, that's understood that that's c at some time, equal log 10 of c naught plus log 10 of this part plus log of this part. So log 10 of exp negative kw as t over v. Now let's apply this guy, and that gets a little tricky, but if you think about it, let's let this whole thing in here be our x. So we have e to the x, so the log of exp to the x equal x. I lost the parentheses here. So if you apply this third equation here, you end up with log 10 of c equal log 10 of c naught minus kw as over v natural log of 10. I'm using this guy here. This is all times t. So now we have this equation, same equation, we just manipulated it mathematically. And now you see that this is the equation for a straight line. If instead of c as a function of time, we plot log 10 of c versus t. Now that's not the same as in Excel, you use a log scale. If you're doing this in Excel, you have a column of c versus time. We'll make another column called log 10 of c and then plot that versus time. And so you see our variable is log 10 of c, here's a log 10 of c naught, and then here's some values times time. So this is a straight line on this kind of a plot, and we have an intercept, and we have this whole thing is the slope of the line. Now if I take the same data that we started with, but I plot log 10 of c versus time. Now time is still linear scale, and this is a linear scale, but we're plotting log 10 of c rather than c. Again, that's not the same as a log scale. It'll look like a log scale. It'll look like a same kind of behavior, but we're plotting a linear scale of log 10c, and then you plot your data. And so what you should get is a nice straight line. What you'll actually have is some scatter. So this will be your original log 10 of c naught right here, and it might not be exactly where this intersects. You're going to have some scatter in your data, and then when we do logs, the scatter down here will be even worse. So here's what we're going to do. We're going to throw out these because those are not reliable data. Way from the beginning we knew that these guys are not very reliable, but the rest of it is very reliable. In fact, what we're going to do then is take all these data and you would do a linear regression analysis and get a straight line. Do a linear fit, not a polynomial of order 1, which is linear. And so you can see that this is a straight line, and recall from high school math that y equal mx plus b is our standard equation for a straight line. And here our equation is this equation that we have up here. Log 10 of c equals, I'm rearranging the terms, negative kw as over v natural log of 10. That's just a constant natural log of 10 times t plus log 10 of c0. When you do a linear regression analysis, this red line is the linear regression analysis line. You see that this b is this, and then we have this slope equal to this whole thing. It's a negative slope because it's decaying, so that makes sense. And then, of course, everything else corresponds here. The x is t, and the y is log 10 of c. So we have a beautiful equation for a straight line. And this is what we care about. This is the slope. We find the slope of this line, which is a negative slope. To get kw now, we simply solve this for kw. We don't really care what the y-intercept is. We just want to make sure we have a decent curve fit, not too much scatter. And so your answer then is kw equal negative this slope that we get from our linear regression analysis times volume times natural log of 10 over as. And now you're able to measure kw. That's pretty slick, I think.
I really like this algebra.
Yes, we all like it too, Albert. Let's do a quick example. a company develops a new fabric, they want to measure the wall loss coefficient. So since you took ME 345, which is now called 348, I used to teach that all the time, how to do linear regression analysis. So you do basically what I just said. You plot like this, you find the slope. So all we need is this equation. We have the area of this fabric, you have the volume of the room air, so this is AS, this is V, and then this is the slope. If you plug in the units, the slope turns out to be 1 over time, whatever time you're using. You can use minutes or seconds or hours. This is mathematically incorrect. You could do the same thing we did with noise. You could actually call this log 10 of C over some C reference, which is equal to 1, so that your mathematicians don't have a hernia over seeing log of something with units in it. All you have to do is plug in the numbers, watch your units, of course. The slope is negative 0.005671 over minutes, and then the volume is 9.90 meter cubed. Natural log of 10 is just a number, no units, and then AS is 4.95 meters squared. You get 0.261 meters per minute. And now you have amazed your supervisor by showing that you know how to do this kind of a measurement because you took some cool courses at Penn State.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3.